Okay, so we're going to start looking now at solution enthalpies with a little bit more expanded on compared to what we were looking at before. So we've looked at reactions that were done in solution, and now we can sort of look at the differences that we see with lattice enthalpies built into those calculations as well. So thinking back to what we've done in energetics previously, okay, we can have a look at this fairly straightforward question. So we're told that a student added 5.35 grams of ammonium chloride to 100 centimetres cubed of water. The initial temperature of the water was 25.55 degrees C, and that it decreased to 21.79 degrees C. From this, we could look at using Q equals mc delta T and work out the amount of heat energy, and then work out the amount of mole of ammonium chloride and work out the enthalpy change that would occur for 1 mole of the solute. Okay, so we would work out 1 mole and go through that. So I want you to have a go and then come back and have a look at those calculations with me. Okay, so hopefully what you realise is that we are having dissolution of an ionic compound, which is what we're seeing here. The ammonium chloride is dissolving, so it will be an endothermic process, which is why the temperature decreased. We can calculate the heat, okay, given off by using Q equals mc delta T, and we'll get negative 1650 joules. Okay, and then the number of mole of ammonium chloride that was in there. So since this was for 0.1 mole, we then want to know what it would be for 1 mole entirely, because that's what the question asked us here. So we would multiply that value, okay, the value that we had here, 1650, essentially we'd multiply that by 10 and it gives us 16,500 joules or 16.5 kilojoules that was absorbed. Okay, if the mass of the solution is assumed, okay, remembering not just the mass of the water, but the mass of the solution being the mass of what was dissolved into it as well, then we get a slightly different value. Okay, so we've talked about how when we use these calculations, delta H of the system, we use the mass of the water or the mass of the solution. So here we're using the mass of the water. If you add in the mass, the entire mass of the solution, which is what we're doing there, then you get a slightly different one, a slightly different value. Okay, both approaches are usually okay within the IB. So if we look at this, we can see that the enthalpy of solution can be calculated by looking at the temperature change as something dissolves, okay, to form a solution. But the solvent and solute interaction depends on the concentration of the solution. So if we want to define a consistent enthalpy value, because concentration has an effect on this, we need to consider the enthalpy at infinite dilution. Okay, so infinite dilution is given by this definition here, that a solution that contains so much solvent that when the more solvent is added, the concentration does not change. Because remembering that how easily something dissolves in, or the concentration of the analytes in the solution will change the enthalpy or change the way they interact or how easily it dissolves, and therefore change the energy of the system. What we're going to do is assume this infinite dilution. Okay, so this is basically that there's so much solvent that the concentration doesn't change, that there is so much water, it doesn't matter what we add in, the overall concentration wouldn't change. Okay, sorry, that was the bell. So when we do this, enthalpy of solution is then stated as being the enthalpy change when 1 mole of a solute is dissolved in a solvent to infinite dilution under standard conditions. Okay, so this is another standard state situation. So when we look at dissolving sodium chloride, going from sodium chloride solid and dissolving it into water, we know this would be an endothermic process. So we have the polarity of the water molecules surrounding the different ions and forming hydration spheres. So this hydration, okay, so when the ions are separated and surrounded by water molecules, they're considered to be hydrated. There is a hydration enthalpy that goes along with this. Again, we're looking at being able to calculate these. So the hydration enthalpy, given in section 20 of your data booklet, is the change that occurs when 1 mole of gaseous ions dissolves to form an infinitely dilute solution of 1 mole of aqueous ion under standard conditions. Okay, so again, we're defining all our conditions. If it's not under standard conditions, it'd be a little bit different. Okay, so because there's a force of attraction between the water and the ions, it's an exothermic process and the enthalpy changes are negative. So the enthalpy of hydration of lithium is given as negative 538, and we get different values depending on the size of the ion and the level of charge. So now, if we can look at the enthalpy change of solution, this can be related both to the lattice enthalpy, how strong the attraction is within the lattice, and the hydration enthalpies of the solution, how much energy we're getting back. All of these form another type of enthalpy cycle. Okay, so the enthalpy of solution at standard conditions of NaCl is the enthalpy, the lattice enthalpy, plus the hydration enthalpy of both of the ions associated. So this endothermic value minus the 2 exothermic values to give the overall enthalpy of the solution. Okay, so we can look at these. The factors that affect the enthalpy of hydration, okay, will be the strength of the attraction between the ions and the water. Okay, so as you can see, aluminium has a high charge, small size, we get a large hydration enthalpy. Okay, whereas lithium, which will be a bit larger and a lower charge, has a lower hydration enthalpy. That's basically it. I want you to read through your textbook and attempt these exercises, and we'll talk about these a little bit more next time we're in class.